will be in this direction. There's a G. So it will flow radially outward, no? So if you show that, this one, if you see the cross-sectional view, no? It's not again a sphere, cross-sectional view it is. Say, calculations are very easy. A student has to just follow the basic rule. Whatever the type of question, I think maximum you can manage. Only if it is some three-dimensional or some based on something like polar coordinates, you may struggle. The most of the things, just you have to apply line integral and you can manage here. How the current will flow? The current will flow radially outward. The current will flow radially outward here. So this will be the A. The current will flow here radially outward. This is positive, negative, put it. I'm not showing the cell. This will be the direction of J, no? And tell me what you should do now. You should assume here a thin cylindrical shell, no? A thin cylindrical shell, you are going to assume it. I'm going to assume a thin cylindrical shell. Here, the cylindrical shell, I can show it here like this. Since colors are possible, that's why I'm just taking help of that one. So what is this assumption now? Thin cylindrical sheet. Thin cylindrical shell, you call it. First we'll define the resistance. Is it justified? Why to assume cylindrical sheet? Because how the current density should be the normal to the, so it will flow radially outward. Then how the elemental surface should be? The elemental surface should be assumed in such a way that the J bar should be directed normal to the elemental surface, what you assume. This is the elemental surface. Okay, now write down the expression for that. What is dr is equal to? Dr is equal to resistivity of material is rho. Okay, we know rho. What is the thickness? Let this be R. Thickness of this be dr. Rho L, no? So the thickness it will see is dr. Then what is the surface area? The surface area directed normal to the current density. That should be called as surface area. So what is the surface area of cylindrical sheet? It should be equal to, the radius should be R. This is the axis. So then 2 pi R into L. So rho 2 pi L you take outside, dr and R. If I integrate this, R equal to rho 2 pi L dr by R. What should be the limit? Should be from A to B. Rho B by rho 2 pi L log of B by A. This will be the resistance of this particular thing. And now I connected a cell. So how much of current will flow here? Current will flowing here will be I. Then expression for I should be equal to E by rho 2 pi L log of B by A. Any good questions can be asked here. Now this will become 2 pi L applied EMF rho log B by, keep it here. I want now expression for current density. I can ask you several questions here. So let me give some points. 1 and 2. So in books, they have just ended up here, but there are several questions can be asked. First, I want expression for current density. So tell me what is the expression for current density? J is equal to, what is the current flowing I? What is the surface area? 2 pi RL. And what is the expression for I? We have already here. So let me write it. 2 pi L R rho log of B by E. So 2 pi L get cancelled. So E by R log of B by E. This will be more troublesome. The questions will be of like this. Find the expression for current density at a distance R from the axis. It is like this. They'll ask you the graph, how the J will vary with R. Rectangular hyperbola. Of course, R should not be 0, no? Because the material itself is present from A to B. And then what about this speed at 192? Try to see the diagram. This speed at 192. Whose help I should take to get this speed? J equal to eta Q VD, no? Look at the current density as it moves.
So rho is also there, sir, in the denominator.
Yeah. Rho. I think I missed it. Okay, fine. Yeah. Okay, this much is there. Now look at this one. This speed at 192. Can you say anything about the disk speed? So directly I'll take help of current density. So current density at 2 will be less compared to 1. Disk speed at 2 will be less than that at 1. J2 less than J1. You must take help of the basics here. Huh? So these are very important. I'm stressing you. Definitely the process will try to stress on these things. In books, we will just stop here only. Yeah? The equation will stop here only. Regarding current density, I'll ask you now potential difference between 1 and 2. So how to calculate potential difference? Now, very best question. Somebody even still they are thinking that conductor must be equipotential. In electrostatics, it is. In electrostatics, that particular condition, that net field inside the conductor due to static charge is 0. But you might now counterattack me, sir. You only said no field will exist due to static charges, no field. Due to dynamic charges, what is the state of electrons here? They'll be under displacement, they'll be having velocity. So the electric field will be non-zero. Why though that electrons are moving? Because of the electric field setup. How the electric field here? So I can tell that the electric field here will be in this direction. Definitely, can you say anything about potential difference? S delta V1, delta V equal to E into dr. How to bring E? We don't know E. This is EMF. Huh? Don't get confused with this. I'm capital E and this symbol are different. This is the EMF of cell. This is the EMF of cell. This is what electric field inside the conductor. Then can we calculate potential difference between 1 to S dV equal to E into dr? But we don't know E, how to bring. So we have formula J equal to, we know J. J equal to what? Like E by rho. So what is the electric field? S, electric field also will vary. Then you calculate potential difference. Then whatever the power dissipated in two thin shells, I'll assume cylindrical shells, power dissipated. So any of